Hello everyone, welcome back. Let's talk about another easy problem on Leetcode today, binary search Leetcode 704. Even though this is an easy problem, it is a foundational one. Mastering it can help tackle a wide range of problems that require efficient searching within a sorted dataset. In this problem, we are given an array of integers, nums, which is sorted in ascending order, and an integer target, and we should write a function to search target in nums. If target exists, then we should return its index, otherwise we should return -1. And we must write this algorithm in O of log n time, O of log n runtime complexity. Then in example 1, for the given nums array and target equal to 9, we will return the answer as 4 because number 9 is present at index 4. Similarly, if target was equal to 2, then we will return -1 because number 2 is not present in the array. Now in terms of solution, one of the naive approach can be that we perform the linear search where we iterate through the array using say a for loop and check each element against a target. If the target is found, then we will return its index, otherwise we will return -1. And this is what is called the linear search. Now the time complexity of this approach is O of n, where n is a number of elements in the array. Since every element may need to be checked, and of course we can do better than this using binary search, and the problem name itself is binary search. Binary search leverages the sorted nature of the array to efficiently search the target. It repeatedly divides the search space in half, narrowing down the possibilities. Let's understand this with an example. In binary search, we take two pointers, say left and right, position at the two ends of the array. Here, for example, left is equal to index 0 and right is equal to index 5. Now we need to calculate the midpoint or middle index to split the search space, and technically both the elements 3 and 5 are in the middle. We calculate the middle point using the formula left plus right by 2, that is 0 plus 5 by 2 equal to 2.5. But since the array indices must be integers, fractional results like 2.5 cannot directly serve as an index. In this case, we have two valid interpretations for the midpoint. First, the nearest integer on the left, which is the floor value. For example, here it will be 2, or the nearest integer on the right, which is the ceiling value, equal to 3 here. To keep our logic simple and consistent, we can use integer division to determine the middle point, avoiding unnecessary complexity of floor and ceiling in the midpoint calculation. So the middle index will be equal to 0 plus 5 by 2 equal to 2. And now we check if the middle element, in this case 3, is equal to target. If it was, then we would have returned the middle index as our answer. However, in this case it is not. At this point, the process seems similar to linear search, checking for the individual elements. But binary search allows us to take advantage of the sorted nature of the array. So what else can we do? We can perform a comparison to narrow our search. Since the target element 9 is greater than the middle element 3 and the array is sorted, it means the target is greater than every element to the left of 3. So as a result, we can eliminate the left half of the array entirely and focus on the search space on the right. So to achieve this, we will move the left pointer here, which is equal to mid plus 1. And now the left pointer is at 3 and the right pointer is at 5. Similarly, if the target was less than the middle element, it would also be less than all the elements to the right of the middle, since the array is sorted. In this case, we will eliminate the right subarray and hence move the right pointer to mid minus 1. So continuing with our iteration, in the search space with left equal to 3 and right equal to 5, we will again calculate the midpoint, which will be equal to 3 plus 5 by 2, which is equal to 4. And again we will check if the middle element is now equal to target, and this time it is. So we will return index 4 as our answer. So by eliminating half of the search space in each step, we found a target index 4 in just 2 iterations, as opposed to 5 iterations with a linear search. This demonstrates the efficiency of the binary search. Now let's look at the case when the target does not exist in the array. Suppose the array has element 11 instead of 9. So now the target element 9 is not equal to the middle element 11, but it is less. This means we should focus on the left subarray. and eliminate the right half. So our right will be equal to mid minus 1 equal to 4 minus 1 equal to 3. So now both the left and right pointers point to index 3. So our middle element will be equal to 3 plus 3 by 2, which will be equal to 3 itself. And now we check if the target is equal to 9, but that is not the case. And since the target element 9 is more than the middle element 5, it is greater than every element on the left of 5. Hence, to find target, we eliminate the left half of the array and focus on the right subarray and move the left pointer to mid plus 1. So now left is equal to 4 and right stays 3. Now since left is more than right, this indicates that the search space is exhausted. Hence the target element cannot be found in the array and we return minus 1. Now the time complexity of this approach is O of log n, where n is the size of the input array. And let's try to understand why is that the case. If the array has n elements, then after the first comparison, if the middle element is not equal to target, we will reject the first half or the second half of the array and we will have n by 2 elements left for the next iteration. In the second iteration, we will break the subproblem further and have only n by 4 elements to deal with. Similarly, after the third iteration, we will have n by 8 elements to deal with. And after the k iterations, we will have n by 2 to the power of k elements to deal with. And in the end, search space is reduced to only one element. In that case, we will either find the answer or not. But in any case, the algorithm will end now. This implies n is equal to 2 to the power of k. And if we take the logarithm on both sides, we will get log n to the base of 2 equal to k. Hence, k or number of iterations or the time complexity of this approach will be O of log n to the base 2. And in terms of space complexity, it will be O of 1 if we are following the iterative solution because we are using few variables like left, right and middle. But in case of recursive approach, the space complexity will be O of log n, which is proportional to the number of iterations, as the extra memory is allocated for each recursive call stack frame, resulting in O of log n space complexity. Here is a quick code walkthrough of the algorithm we just talked about with Java code on the left and Python on right. We can implement this algorithm using either a recursive approach or an iterative approach. Here we will solve it using iterative approach as it avoids recursive overhead and it's more memory efficient. If you are interested in the recursive approach, please check the code link in the description below. However, the logic remains largely the same except the recursive version uses function calls instead of a loop. First, let's initialize the left and right pointers to the start and end of the array. Now we will enter the while loop which continues as long as the left pointer is less than or equal to the right pointer and calculate the middle index by summing up left and right and dividing them by 2. In Java, we can use division operator, but in Python, we should use floor division operator, which is denoted by // as the regular division operator does the floating point division, but here we want the integer division. This formula will work in most scenarios to find the middle element of the current search space. However, when the left and right elements are large numbers close to maximum values, like integer.max value in Java or sys.max size in Python for integers, left plus right can exceed the maximum integer limit, leading to the overflow. For example, if left is 2 billion and right is 2 billion and 1, and now if we try to calculate the mid, first we will do left plus right and then divide by 2. So when we are summing up these numbers, we will get 4 billion and 1, which will exceed Java's integer.max value, which is roughly 2.1 billion and cause the overflow. In Python, it will not cause the overflow, but this formula still introduces potential inaccuracies when working with extremely large ranges. To overcome this, we first calculate the distance between the left and right pointers, which is simply right minus left. Now the midpoint between these two pointers will be located at half the distance from the left pointer. To find it, we just add left to the right minus left by 2, which gives us the midpoint. This approach ensures we avoid directly summing up left and right, thereby preventing any chance of overflow. This issue is not a limitation of the binary search as an algorithm, but rather an edge case of how integers are implemented in these programming languages. Continuing with the code walkthrough, we calculate the midpoint using this subtraction-based formula, preventing the integer overflow. Now, if the element at the middle index is equal to the target, we will return the middle index. But if the element at the middle index is greater than the target, we update the right pointer to mid minus 1, eliminating the search on the right side. But if the element at the middle index is less than target, then we will update the left pointer to middle plus 1, eliminating the left side elements. And if the loop completes without finding the target, we will return minus 1. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.